All right, things are about to get crazy. We're about to dabble in some stuff that is a little bit tricky. Just realizing I did not write something down on the previous problem that is not going to impact your life, but just for the sake of my own notes, I feel like, oh, I should do it here too. There we go. Now, we can continue. Here we go. F prime of x. Okay, we're about to do something wild and crazy, but before we do something wild and crazy, let's actually write down what f prime of x is. We can get the equation of this. We really can. It's an upside down parabola, so negative, and then somebody got squared because it's a parabola, and that's the highest degree we'll see. There is no horizontal shift, so it is x squared. And I want to figure out what the coefficient is, and I'm just going to go ahead and tell you what the coefficient is. It's 1, negative 1. Of course, negative because it's upside down. But if you start at the vertex and you count, in this case, down 1 and over 1, you get, well, the slope of 1 in this little region right here. The average rate of change is 1. And in a parabola, that lets you know what that is. All right, in this case, it's 1. I'm just throwing that out there. So going over 1 and down 1, or in this case, you could go to the right 1 and down 1, and it would be 1. Anyway, I digress. Trust me, this is it. Now, this is not it because there's a vertical shift. Okay? Vertical shift is 1. So if I confused you about this understood negative 1, I apologize. But trust me, it works because if you were to plug this into a calculator, you would get x-intercepts at negative 1 and 1. You could solve this by hand and you'll get x-intercepts at negative 1 and 1, which is consistent. So there we go. Let us proceed by finding the derivative, and we'll just graph the derivative. And if you want to do it a different way, that is fine, and I will talk about that in a second. But it's negative 2x plus 0. And the graph of that is going to have an x-intercept of, surprise, surprise, 0. Ah, interesting. So the derivative has a maximum. Let me rephrase it in this case. The derivative equals I gotta be wordy with this one. The rate of change of what we're looking at equals 0 at x equals 0. Therefore, when we graph the derivative of what we're looking at, which means we're gonna graph the second derivative, we'll have an x-intercept at 0. Let me say it one more time in a different way. You have a maximum here, and it is a smooth curve. Therefore, when you graph the derivative of this, which is itself a derivative, graph the second derivative, you're going to cross the x-axis in that same x value. Okay? All right. Now that I've thoroughly confused everyone with the way I word things, let's proceed by drawing this line. Okay, fun. Notice, and again, I think it's worth pointing out, second derivative, I think it's worth pointing out that this graph that we're looking at, green graph, is decreasing. So if you wanted to go really crazy on this, and you could say, watch this, I'm having too much fun here. If I graphed the third derivative, it would be negative 2, which is down here, consistently negative 2, always negative. Therefore, the first derivative is concave down. All right, this is going to be really wordy, but two derivatives later, let me word it funny. The second derivative of the first derivative, which is the third derivative, is negative. Therefore, the first derivative is concave down. Notice it's always concave down, all right? Now, let's talk original. Woo, man, getting confusing. Let's talk derivative and green. The black graph originally on your paper, which is the derivative, increasing. The derivative of that is positive. Decreasing, but positive. Decreasing, which means this derivative is negative. All right. This piece of what you were given, which is a derivative, is decreasing. Therefore, its derivative, the second derivative, is negative below the x-axis. And also, again, decreasing, which is consistent with what you see in red. Now things get really fun. What's the original function? We're about to go there. We're about to go there, and we're not even in that unit yet, but it's going to be fun. So check this out. You know it's cubed, right? Really, notice this. 3, 2, 1, 0. I'm looking at my exponents. Okay, well. Okay. Well, I know it's negative something. So here's the deal. If I took the derivative of this, I'd get that term. So negative something times 3 gives me negative 1. Let's just ignore the negatives for a second. Something times 3 gives me 1. What times 3, what, it's going to go here. The answer to my question is about to get written right here. What times 3 will give me 1? Oh, I don't want to write it because I want you to make sure you get it too. There it is. Okay. The derivative of what is 1? Okay. Notice this is 1x to the 1. I'm sorry, 1x to the 0. So up here we have 1x to the 1. The derivative of 1x gives me 1. Okay? And maybe, just maybe, there was another number here. Maybe it's 5. Maybe it's 55. Maybe it's 555. I don't know what it is. I'm going to call it C for constant. We are playing with antiderivatives now. Oh, man. It's great. It is so great. All right. My calculator's on the other side of the room. If you'll give me about 2 seconds to grab it. 1, 2. Still 2. Okay, good. Got it. I'm going to graph this, and I want to show you some really cool things. But before I show you some really cool things, man, you're going to love this. Derivative has an x-intercept at -1. Therefore, we have on the original function a place where the slope of this is equal to 0 at -1. That was poorly worded. Let me try it again. I'm trying. Okay. This point. I am about to draw what is the equivalent. I'm back on the front side now. I'm about to draw that dot. That dot corresponded to a maximum. Or at the very least a place where the derivative equaled 0. So check it out. That dot are going to correspond to a maximum or a minimum, or maybe it's a minimum and then a maximum, or maybe, just maybe, it could be one of these little funky things like that where the slope is actually equal to 0. I've drawn all kinds of possibilities, or maybe it goes the other way. Maybe it does this. Maybe it's on this side. Maybe it's on, who knows what it is. But the slope at -1 is going to be 0, and the slope at +1 is going to be 0. Let me erase some stuff. The original function, oh, check it out. I hadn't even graphed it yet, and I'm so excited. The original function, f, will be decreasing on this interval because its derivative is negative. Increasing on this interval because its derivative is positive. Decreasing on this interval because its derivative is negative. I'm going to graph it, and I'm just going to make up a number for C. So here we go. Oh, my goodness, y'all, you're going to love this. You're going to love it. -1/3. Let's make that -1/3. X cubed. We'll just do it that way. Plus 1x plus, who cares what, okay? Doesn't matter, but I want it to be kind of visible. And I'm also going to graph -x² plus 1. That's that one. I'm not going to graph the other two. Things get a little clunky. I'm going to change this color to black to be consistent with what we're seeing. There we go. You can do that, by the way. Fun stuff, isn't it? And if I wanted to, I could graph the derivative of that in green and then red, and then we'd have all kinds of fun stuff. And this actually is going to go from -2 to 2, -2 to, we'll just send it up to 2. So -2 to 2, -2 to 2, and I'm just going to graph what we see here. This is my original function. This is my derivative. Okay? Now maybe, just maybe, my original function is not this. Maybe my original function, I'm going to put it down here on this one because it's also blue, is negative 1/3 x cubed plus x minus 1.2. Maybe it's that. But whatever it is, it has, and check it out, check it out, check it out, check it out. It has a minimum at x equals -1 and a maximum at x equals +1. Whatever you choose C to be, it's going to be a minimum here and a maximum here. And here is why. Man. Or the derivative changes from negative to positive here. Therefore, the original graph will be decreasing, then increasing, and therefore will have a minimum at x equals -1. I'm not writing it down, but I'm articulating it. Here goes. Let's try it again. Derivative, negative then positive. Therefore, original function, decreasing, then increasing. Okay? This is a minimum. All right, derivative, positive, then negative. Therefore, the original function will be increasing, then decreasing. That is going to be a maximum. All right, let's draw it. Does not have to be perfect. It does not by any means have to be perfect. And I'm just going to draw, and it's just going to be a little bit, ooh, oh, that's awful. All that work to be so careful about it, and then it looks so terrible. There we go. Tried so hard. Ooh, that is disgusting. It doesn't look like that at all. I'm ashamed of my graph. What have I done? You're fulfilling your destiny, Anakin. Oh, what a disgusting graph I have drawn. That's not much better. That's terrible. The explanations were clear, the graphs were beautiful, and then I drew this one. Shouldn't be quite that flat down there, but there we go. It shouldn't be quite that flat down there because we actually have a shift in concavity, and this is worth talking about too. Let's get that whiteout back out. We're gonna fix this thing. We're gonna fix it real good. That's bad grammar. We're gonna fix it. Make it pretty. You're going to be pretty, and you're going to get a graphical makeover, and you're going to like it. Still not perfect, but a little better than it was. Tempted to start this video over, but dang it, 13 minutes into it. I'm not going to stop it now. All right, notice the change in concavity. It's probably better on this than it is on that, but concave up. Second derivative is positive. See it? See it? Green, positive. Concave up, second derivative is positive. Concave down, second derivative is negative. There we go.